Compact desalination machines are physical machines small enough to sit near a shoreline, a harbour, a clinic, a neighbourhood pump station, or an industrial site. They do not replace large plants everywhere, but they move the act of making fresh water much closer to where fresh water is actually used. Most people hear the word desalination and imagine something huge and remote, like a massive plant somewhere far away that quietly feeds water into pipes they never see. Water problems usually show up in specific places, as pressure drops, contamination events, or supply interruptions, rather than as a simple lack of water overall. Local water production causes outages and restrictions to affect smaller areas instead of entire regions at once. At a basic level, a desalination machine does one job. It takes seawater and separates the water from the salt dissolved inside the seawater. Salt is dissolved into the water as charged particles that stay mixed unless something forces the charged particles apart. Any desalination machine has to do physical work to make that separation happen. Even with a well-designed machine, salt and water naturally remain mixed, so it must continuously force separation during operation, and that continuous effort affects how it has to be built and run. As a result, running it always consumes power and creates wear that operators have to plan around. Most compact desalination machines use one of two approaches. One approach uses pressure. Seawater is pushed at very high pressure through a membrane with pores so small that water molecules can pass but salt ions cannot. The other approach uses heat. Seawater is heated until water turns into vapor, and the vapor is then condensed back into liquid, leaving salt behind. Both approaches work. Pressure systems rely on membranes that can clog or wear out. Thermal systems rely on heat transfer surfaces that can collect mineral buildup. The decision is about choosing which kinds of problems can realistically be managed in a small local machine. That choice directly affects maintenance schedules and downtime frequency. Please subscribe. Historically, desalination has been centralized because energy and maintenance are easier to manage at large scale. Large plants can justify enormous pumps, complex pretreatment systems, and teams of trained operators who constantly monitor performance. Compact machines do not have that luxury. They are often placed in locations with limited space, limited staffing, and imperfect operating conditions. They have to keep working through power interruptions, uneven maintenance, and changes in water quality. The problem compact desalination machines are meant to solve is practical. Many coastal communities sit beside an unlimited supply of water that they cannot directly use. Fresh water is often transported long distances through pipes, pumping stations, storage tanks, and pressure regulators. Every one of those components can fail. A broken pipe miles away can reduce pressure everywhere downstream. A pump outage can empty storage faster than expected. When supply is centralized, a single failure can affect many people at once. Compact desalination spreads water production across many smaller locations. This reduces how many people lose water when one part of the system fails. What makes compact desalination especially difficult is the condition of the water going into the machine. Seawater contains sand, silt, organic material, microorganisms, and debris that change day by day. If untreated seawater reaches a membrane system, the membrane will foul. When that happens, the membrane pores begin to clog. Pressure inside the system rises, water flow drops, and energy use increases. Over time, less and less water comes out. The machine may still be running, but it is no longer doing useful work. Preventing this outcome requires pre-treatment stages that remove particles before they reach sensitive components, and each added pre-treatment stage introduces more parts that can clog or fail. If pre-treatment is neglected, water output can drop without obvious warning. Thermal compact systems avoid membrane fouling but face different problems. When seawater is heated, dissolved minerals can come out of solution and coat internal surfaces. That mineral coating blocks heat transfer and forces the system to work harder to produce the same amount of water. As mineral buildup grows, system parts experience more stress and wear. Temperatures and flow rates have to be controlled carefully, and cleaning has to be done on a regular schedule. If those maintenance steps are skipped, output can fall quickly, even though the system does not appear broken. This can lead to sudden water shortages even while the equipment still looks operational. Separating salt from water always requires energy. No desalination design avoids this requirement. Engineers can reduce wasted energy and recover some of it inside the system, but water production still depends on a steady supply of power. In compact systems, power quality becomes important. Frequent on and off cycling wears out pumps and membranes. Voltage fluctuations can interfere with control electronics. Even a well-designed machine will struggle if the power feeding it is unstable. In real use, unstable power often translates directly into lower water output. When salt is removed from seawater, it does not disappear. It ends up concentrated in a brine stream. That brine stream has to be discharged or managed. In compact installations, space is limited, and intake and discharge points cannot always be placed far apart. If concentrated brine is released too close to where water is drawn in, the machine can start pulling in saltier water than intended. Pulling in saltier water increases energy demand and speeds up corrosion and mineral buildup. The physical layout of the site affects performance just as much as the components inside the machine. Poor layout can shorten equipment life and raise operating costs. Compact desalination is not meant to replace large municipal systems that serve entire cities. The value of compact desalination comes from being local. A port facility can keep operations running during supply interruptions. A clinic can maintain water availability when pressure drops elsewhere. A coastal town can reduce dependence on a single distant source. The benefit is not unlimited water, but smaller failures that are easier to isolate and faster to fix. This improves day-to-day reliability even when total supply is limited. Compact desalination always involves trade-offs. Filters need replacement, membranes need cleaning, pumps wear out, and salt constantly attacks materials. These machines usually cost more per unit of water than large plants, but they reduce the need to move water over long distances and limit how far failures spread. The limits set by energy requirements, material durability, and ongoing maintenance determine where compact desalination makes sense and where it does not. Water production can happen close enough to daily life that problems become smaller, more visible, and easier to manage when problems occur. For users, this often means fewer surprise outages and clearer maintenance decisions. Thank you very much for watching. Please like and subscribe.